This is Catherine Schmer at Chattanooga State Community College, and this is video 2 of the dot product. In this video, we'll talk about vector projections, which is one application of our dot product. So a vector projection is when we have two vectors, let's call them u and v, and I'm going to draw v as a longer vector. It doesn't necessarily have to be, but in this picture it is. And u is a vector that makes some angle with v. We don't know what angle, but in this case we're drawing u with the same starting point as v up above v. Now what I'm going to do is, it's as if I'm shining a light on vector u, and I'm trying to figure out what the shadow would look like in the direction of vector v. So I make a 90-degree, I drop down a line and make a 90-degree angle with vector v, and the vector that results, the shadow of u, is the vector projection of u projected onto vector v. So the way we write that is proj and then a subscript with vector v and then vector u in normal font. So it's u onto v. That's how I remember which one's the big one and which one's the small one. V is small as a subscript because u is going onto v. Now this angle always has to be 90 degrees in order to do a vector projection. Okay, so let's get into the details of it. The scalar component of u in the direction of v is SCAL, so scalar, subscript v, and then regular script u, so scalar component of u onto v, and it's equal to u dot v over the magnitude of v. So that's your formula to find the scalar component of u in the direction of v, or in other words, the length of that vector projection. It's the length of that shadow of u on v. The vector projection of u onto v is proj subscript v regular script u, so the projection of u onto v, and it's equal to u dot v divided by the magnitude of v, so that scalar component, the length, times v divided by magnitude of v. So you're taking the scalar component, the length of it, and you're multiplying by the unit vector in the direction of v. Now usually you see the formula slightly differently, and it's just the simplified version of this. So this simplifies to the projection of u onto v equals u dot v divided by the magnitude of v squared times vector v. So that is the formula that we usually use in application. So let's do example 2 from the guided notes. We want to find the scalar and vector projections of u onto v, given that vector u is 2i plus 2j plus k, and vector v is 2i plus 10j minus 11k. Okay, so first thing I need is u dot v. So I'm going to multiply the I components together plus the j components multiplied together plus the k components multiplied together. So 2 times 2 plus 2 times 10 plus 1 times negative 11, and that equals 13. So there's my dot product of u and v. Now I'm doing u onto v, so that means I need the magnitude of v. So the magnitude of v is the square root of 4 plus 100 plus 121, and that simplifies to square root of 225, which is equal to 15. And remember, to get that I just squared each component of v, added them together underneath the radical. Now, from the formula, the scalar component of u onto v is equal to u dot v over the magnitude of v. So now I'm going to plug in the numbers that I found. That's 13 divided by 15. So that wasn't too bad. Now we have to take that, apply it to the projection of u onto v. So the projection of u onto v is equal to u dot v divided by the magnitude of v squared times vector v. So 13 over 225, so I squared the magnitude of v, times vector v, so I multiply the 13 over 225 times 2i plus 10j minus 11k, and I distribute, so I get 26 over 225i plus 130 over 225j minus 143 over 225k. And then, of course, when you're giving your answer, you want to simplify the fractions if possible. In this case, the 130 over 225j could simplify, and you want to check each of your fractions to see if they could simplify.